Let's talk a little bit about energy diagrams. Energy diagrams are a way of us showing how much energy was in the reactants versus the products. And it also kind of shows us if this reaction might just go ahead and proceed without me having to do anything. So for a reaction to occur, two molecules have got to collide with enough kinetic energy, energy in motion, to break bonds. Okay? So they have to collide in such a way that B will be bumped off, A will be left, and then B and C can then form a bond. The other thing is, in addition to enough kinetic energy, is the orientation has to be correct as well. That is, it has to hit at the right angle. So if it hits at the right angle, okay, to knock that off, then it would break the bonds and then allow this bond to then be made. If it hit at kind of a wrong angle to the side or whatever, then it may not be enough force in order for that to happen. So the two things that must occur for the reaction to begin is you have to have enough energy to break the bonds, and you have to collide with the right orientation, the right angle. And so we write energy diagrams that sort of show us what's going on with this. So in the energy diagram, what you have is you'll have the reactants on one end, and this is energy increasing. So you have reactants, and so in this case, for example, you have A and B, which is a compound, plus C, and this is how much energy it takes in order for that reaction to get started. And so this is something called E sub A, and E sub A is the activation energy, or energy of activation. It's the difference between the energy level of the reactants and the energy of what we call the transition state. The transition state is basically where you got to get to in order for the reaction to continue. And so it's that top of the hill, like the roller coaster. So if you get to that point, then the reaction is going to proceed. So the energy here has got to get to the transition state, and that's what's called our energy of activation. Notice I'm showing you here as well the delta H. The change in energy is going to be where the energy started with the reactants and where it ends up with the products. So you can see in this particular case that the energy is lower in the products than in the reactants. So since we ended up lower, it's going to be a negative delta H, which means it's also what? Exothermic. So the activation energy is the minimum amount of energy that it takes for the reaction to occur. It's called the energy barrier because this height of that curve we were just looking at determines the reaction rate. So how hard it is to get up to that transition place, that energy barrier, that's what's going to be dictating how fast this reaction can occur. When the activation energy is high, few molecules have enough energy to cross that barrier, so the reaction is slow. When the activation energy is low, however, there's a lot of molecules that have enough energy that can cross that, get to that transition state, and the reaction is fast. The difference in energy, as I showed you a minute ago, is this delta H, where you have an energy level at the beginning with the reactants, and then there's an energy level where you get to the end. And so that delta H, in this case, they're saying is a negative 10 kilocalories. And since it's negative, it's exothermic. In a delta H that's positive, that's an endothermic reaction, And so the energy of the products is higher than the energy of the reactants. And so look how much higher this energy barrier is, or the activation energy is, before it can get to where it's going to proceed with that reaction. And so that's why you have to add heat or add energy in order for an endothermic reaction to proceed.